For centuries, Mars has captivated human imagination. The fourth planet from our Sun, Mars sits approximately 225 million kilometers from Earth at its closest approach. This crimson world, with its polar ice caps and ancient valley networks, has long whispered promises of possibility. Today, space agencies like NASA and ESA, along with private companies like SpaceX, are actively planning human missions to Mars. NASA aims for a crewed mission in the 2030s or early 2040s. The vision is clear: make humanity a multi-planetary species. But Mars is not a welcoming world. It is fundamentally hostile to human life in ways that challenge our current technology and understanding. The question isn't whether we will try to reach Mars. We will. The real question is, are we truly ready? The journey to Mars takes approximately 7 months using current propulsion technology. During this time, astronauts would be confined to a spacecraft smaller than most apartments, traveling through the vacuum of space at speeds exceeding 20,000 kilometers per hour. According to NASA's Curiosity rover measurements, astronauts on a round-trip Mars mission lasting 180 days each way plus 500 days on the surface would be exposed to approximately 1 sievert of radiation. To put this in perspective, the European Space Agency limits astronaut career exposure to 1 sievert, associated with a 5% increase in lifetime fatal cancer risk. Mars presents extreme environmental challenges. The average surface temperature is -63 degrees Celsius, with winter temperatures at the poles dropping to -125 degrees Celsius. During summer at the equator, temperatures can reach a comfortable 20 degrees Celsius, but nights plunge back below freezing. The Martian atmosphere is only 0.6% as dense as Earth's atmosphere at sea level. It consists of 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only 0.13% oxygen. A human exposed to this atmosphere without a pressure suit would lose consciousness within 15 seconds and die within 2 minutes. Mars experiences planet-wide dust storms that can last for months. In 2018, a global dust storm persisted for over 3 months, completely blocking sunlight and shutting down NASA's Opportunity rover after 15 years of operation. The Martian dust is extremely fine, smaller than talcum powder, and toxic, containing perchlorates harmful to humans. Mars has no global magnetic field and an atmosphere only 1% as thick as Earth's. This means the planet offers virtually no protection from cosmic radiation. NASA's Radiation Assessment Detector on Curiosity found that astronauts on the Martian surface would receive approximately 0.67 millisieverts of radiation per day, compared to 0.4 to 1.0 millisieverts experienced by astronauts on the International Space Station. The journey through space is even more dangerous. During the 8-month transit, astronauts would be exposed to approximately 1.84 millisieverts per day, nearly 3 times the dose on the Martian surface. According to ESA data from the ExoMars Trace Gas Orbiter, a 6-month journey to Mars could expose astronauts to at least 60% of their recommended entire career radiation dose limit. This radiation damage accumulates silently. It breaks DNA strands, increases cancer risk, damages the central nervous system, weakens the immune system, and can cause cataracts. ESA physicist Marco Durante explains, "One day in space is equivalent to the radiation received on Earth for a whole year." Constructing habitats on Mars presents enormous challenges. Current estimates suggest it costs between $50,000 and $200,000 to transport just 1 kilogram of material to Mars. A modest house on Earth weighing 80,000 kilograms would cost approximately $4 billion to ship to Mars for a single structure. Current solutions include inflatable habitats tested on the International Space Station and 3D printed structures using Martian regolith, the soil on Mars's surface. However, Martian regolith contains toxic perchlorates and cannot be used directly. Advanced chemical processing would be required to make it safe for construction. Generating breathable air on Mars is critical. NASA's MOXIE experiment on the Perseverance rover has successfully demonstrated oxygen production from Mars's carbon dioxide atmosphere. MOXIE produces approximately 10 grams of oxygen per hour, enough for a human to breathe for about 20 minutes. Scaled-up versions could support a small colony. Water exists on Mars, primarily as ice near the poles and buried beneath the surface. Extracting, melting, and purifying this water requires significant energy. Every drop must be recycled continuously. The International Space Station currently recycles approximately 90% of water and air. Next-generation systems aim for 98 to 99% efficiency. Mars is waiting. The challenges are real and substantial. But humanity has always looked at the impossible and said, "Watch us." The journey to Mars will be long, difficult, and costly. It may take longer than optimistic predictions suggest. But if history teaches us anything, it's that humans don't accept limits easily. The first human footsteps on Mars will mark not the end of a journey, but the beginning of a new chapter in human history. Whether that happens in 20 years or 50, the work we do today, the research, the testing, the incremental progress, brings that moment closer. Mars colonization is not impossible, but it is extraordinarily difficult. We must approach it with eyes wide open, understanding the true scale of the challenge. We must respect the science, acknowledge the risks, and commit to solving problems we don't yet fully understand. Only then can we make Mars not just a destination, but a home. The journey to Mars begins not with a rocket launch, but with honest recognition of what lies ahead. The psychological challenges are severe. Communication with Earth has a minimum 12.5-minute delay each way, 25 minutes for a round-trip message. When Mars is on the opposite side of the Sun from Earth, communication can be blocked entirely. Astronauts would experience profound isolation unlike anything humans have faced before. Studies of Antarctic research stations and long-duration spaceflight reveal predictable psychological patterns. The third quarter phenomenon occurs when morale crashes about 3/4 through a mission. Crew members become withdrawn, irritable, and less motivated. For a Mars mission, this would occur precisely when sharp focus is most needed. Mars's gravity is only 38% of Earth's. Prolonged exposure to low gravity causes muscle atrophy and bone density loss of up to 1 to 2% per month. Astronauts on the International Space Station exercise 2 hours daily just to slow, not stop, this deterioration. On Mars, for years or permanently, the effects would be profound. Medical emergencies pose catastrophic risks. There are no hospitals, no specialists, no advanced diagnostic equipment. A condition as simple as appendicitis could become fatal. With the 25-minute communication delay, real-time consultation with Earth doctors is impossible. Crew members would face life-or-death decisions with limited resources and training. Despite these challenges, progress is being made. Researchers are developing hydrogen-rich polymer materials that could reduce radiation exposure by 30 to 40%. Electromagnetic field generators could create artificial mini-magnetospheres around habitats, mimicking Earth's protective magnetic field. Autonomous robots could be sent ahead of human missions to construct habitats, extract resources, and establish infrastructure using 3D printing technology and Martian materials. By the time astronauts arrive, basic life support systems could already be operational, significantly reducing risk. Advanced hydroponic and aeroponic systems are being perfected for growing food with minimal water. Scientists are engineering crop varieties specifically for Martian conditions. Plants that can tolerate low pressure, high carbon dioxide, and artificial lighting while producing maximum calories with minimal inputs. Research into pharmaceutical interventions shows promise. Drugs that help cells repair radiation damage more effectively could reduce cancer risk. While these technologies are in early stages, they represent genuine pathways toward making Mars colonization possible. According to a 2018 NASA study, terraforming Mars, making it Earth-like with a breathable atmosphere, is not possible using current technology. Lead researcher Bruce Jakosky stated clearly, "Terraforming Mars is not possible using present-day technology. Mars lacks sufficient carbon dioxide to create a thick atmosphere even if we released all available CO2. ESA radiation expert Marco Durante states, "As it stands today, we can't go to Mars due to radiation. It would be impossible to meet acceptable dose limits. This represents one of the most fundamental barriers to long-term Mars habitation that current technology cannot fully solve. The cost is staggering. Returning to the Moon was estimated in 2005 to cost $104 billion, equivalent to about $170 billion in 2025. A Mars mission would cost substantially more. SpaceX's Elon Musk estimates needing 1 million people paying $200,000 each just for the colonization phase, not including the vast infrastructure costs before anyone leaves Earth. NASA's current plans target a crewed Mars mission in the 2030s or early 2040s. However, this would be primarily an exploration mission, not colonization. Establishing permanent, self-sustaining settlements would take decades beyond the first landing. Recent budget challenges and technical delays make even these timelines uncertain. In 2025, President Trump proposed reducing NASA's 2026 budget by 23.8%, though the Senate maintained funding near 2025 levels. These political and financial uncertainties affect the pace of Mars exploration development. Scientific readiness and political will do not always align. So why aren't we ready to live on Mars? Because Mars is fundamentally, profoundly hostile to human life. Because every breath, every meal, every moment of survival requires technology functioning perfectly in an environment designed to kill us. Because the radiation exposure alone presents risks we cannot yet fully mitigate. Because the distance is vast, the challenges are immense, and the unknowns are substantial. We are not ready today. But every day, engineers solve problems. Scientists make breakthroughs. We test new materials, refine processes, and push boundaries. The generation that will walk on Mars may already be in school, learning the science that will take them there.